Hi, welcome back. We're up to lecture 17, and the topic in today's lecture is factorial ANOVA. So in the last lecture, we covered an introduction to ANOVA via a one-way between groups ANOVA. Now we're going to add in a second independent variable and cover factorial ANOVA. So in a factorial ANOVA, we'll have two independent variables and one continuous dependent variable. So let me start with an example, and I'm going to move away from the working memory training example. I think we've had enough of that. And I also like this example because it really conveys the idea of an interaction. And it's based on real research, which is a very productive line of research in cognitive science that started about 10 years ago. This experiment that I'm going to base this example on was published in 2001. So, of course, we're all concerned with the hazards of talking on a cell phone or mobile phone while driving. So people set out to examine this in a systematic way via randomized controlled experiments by putting people in a driving simulator and then randomly assigning them to different conditions. So one independent variable in this example is just driving difficulty. So there's a driving simulator, and you can vary the difficulty of the road. So some is really easy, not a lot of traffic, and then there's a hard simulator where there's lots of traffic, lots of turns, and so on. The other variable that's manipulated is conversation demand. So, and this is the really interesting part of this research, which I'll sort of get to at the end after the statistics piece. It actually really matters what the content of the conversation is. Turns out that matters more than whether your cell phone is hands-free or you're holding it. The content of the conversation really matters. So that's another independent variable that was manipulated in one of these early experiments. And then they looked at the number of errors that people made while they were in this driving simulator. And I'm just going to give away the results right away, just so I can introduce some of the terminology in factorial ANOVA. So here are the results in a bar plot, and what I have plotted down here is conversation demand. So there's a control group that was engaged in no conversation while driving, then a sort of low demand group and a high demand group. And later I'll explain the distinction. For now, just trust me, they were sort of differing in demands. And then the driving simulator, that was either easy or difficult. I want to point out several things in this graph. One, you can just ask, is the effect of the driving difficulty, is that having an impact? And well, yeah, it is. So the orange bars, if they're orange, versus the grayish green bars, so these orange bars are higher than the darker bars. And that's by design, right? So they made the difficult driving simulator more difficult so that it would result in more errors. So that's not surprising. You can also just say, does conversation make a difference? So if I just want to look at sort of these two together versus these two together and these two together, it looks like just conversation by itself matters, right? So more demanding conversation, more errors. But the most important piece here, and this is the new concept in this lecture, is that these two variables interact to produce more errors. So you can see that the difference, there's hardly any difference here, bigger difference here, and the difference gets even larger at the high demand conversation condition. Conversation demand and driving difficulty interact to produce more errors. And that's actually, there's lots of research to support that idea, and it's a nice illustration of a true interaction. Another good example of interaction, you can think of drug studies. So if you take two drugs at once, we could do a study where you're assigned to either placebo or drug A or placebo in drug B, and maybe the only effective treatment is if you're in drug A and drug B condition. Maybe the drugs need to interact to work. It's another good example of interaction. So in a factorial ANOVA with two independent variables, we can test three hypotheses. So 1, were there more errors in the difficult driving simulator? 2, were there more errors as conversation demand went up? And 3, do they interact? So what that means is this factorial ANOVA, this analysis is going to produce 3 F ratios. And I'm going to call them F sub A, F sub B, and F sub A by B. So A is just the first independent variable, B is the second. And I'm going to put in driving difficulty as the first, conversation demand as the second. And that's arbitrary, it doesn't matter, we could do it either way. Let me just walk you through a couple definitions so that we're all clear. I've taught this material many, many times and students mix up these definitions, so just make sure you don't. A main effect in the context of a factorial ANOVA just refers to the effect of one independent variable ignoring the other one. So a main effect is exactly what we looked at when we did a one-way ANOVA. Just imagine you only have one of the IVs at play. So just conversation demand. Is there a main effect of conversation demand? Just ignore the other independent variable. That's a main effect. I could look at the main effect again in the graph. I did it just a second ago, but like here's the main effect of conversation demand. Looks like there's a significant effect. We'll see later when we look at the output. Of course, the important new concept is an interaction effect. That's when the effect of one independent variable depends on the other. This is exactly like a moderation effect in multiple regression, right? Remember multiple regression where we had, say, a correlation between x and y, and then it varied as a function of z. We called that moderation. Same exact thing here, and under the hood, the general linear model, it's treating it exactly the same. It's just an experimental research in ANOVA. We call it an interaction effect. In correlational research in multiple regression, we call it a moderation effect. Basically the same thing. The effect of one IV depends on the other, or the effect of one predictor depends on the other. Another way to say that is in terms of simple effects. So this piece in parentheses. The simple effect of one IV changes across the levels of the other. Well, what's a simple effect? Let me bring you back to the bar plot in a second. A simple effect is just the effect of one IV at a particular level of the other IV. Notice how that's different from a main effect. A main effect is the effect of one independent variable ignoring the other one. This is the effect of one independent variable at a particular level of the other one. So now I could say, well, did conversation demand have an impact in the difficult driving simulator? That's a simple effect. And if the simple effects change as a function of the other IV, then you've got an interaction. And that's exactly what you see in this example. So look at the effect of conversation demand in the easy driving simulator. So this guy, this guy, this guy, not much of an effect. It's going up a little with conversation demand, but not much, especially relative to the orange or lighter bars, right? And it's really going up. So the simple effect of conversation demand is different at each level of driving difficulty. Another thing to keep in mind with factorial ANOVA is that the main effects and the interaction effect, they're independent of one another. They're orthogonal. That is, they're uncorrelated. So I could have main effects and have an interaction, or have main effects and no interaction. They're unrelated. They're orthogonal or independent by design, right? So subjects come into a lab and they're randomly assigned to one of these conditions, and if we randomly assign an equal number of subjects to all of our conditions, then these things are independent by design. That's the beauty of it, and that's why we can test 3 hypotheses in one experiment. And also remember, this is just a special case of multiple regression. It's a multiple regression where the predictors are not correlated. That's sweet. When we did those complicated examples back in multiple regression with moderation and all that, we had correlated predictors, right? X1, X2, X and Z and the product, they could be correlated, which made it hard to disentangle the effects that each predictor was having on the outcome variable. Here it's very straightforward, and the math is very straightforward. So it's just a special case of the GLM. So it's nice in that computationally everything partitions beautifully and adds up nicely. So just as in the one-way ANOVA where we could add up the degrees of freedom and the sums of squares, we can do that here. It's just now we have sums of squares for the first independent variable, for the second, for the interaction, and then for error, which I'm going to write S within AB because subjects are within a group that's defined by a level of A and a level of B, right? So you could luck out and get the no conversation, easy driving simulator, or you could get the really challenging condition and get demanding conversation, difficult driving simulator. So you're a subject within a condition AB. If we want to look at it in terms of Venn diagrams like we did with multiple regression, we could think of the outcome variable y. Here's the variance in y, and some of that variance is predicted by x1, x2, and x3. That's the general linear model, right? So that looks like an old regression example, but just plug in A, B, and the interaction for x1, x2, x3. That's exactly what's going on here. It is a GLM, and ANOVA is using the GLM framework. And again, think of it as a multiple regression that's special. It's special in that the predictors are independent by design. So again, we're going to get 3 F ratios. Every time an F ratio is just going to be one mean squares relative to another mean squares. Our unsystematic variance is just variance within a group, so subjects within AB. So that's always going to be the denominator for each F ratio. The others are just mean squares sub A, mean squares sub B, and mean squares for the interaction. Mean squares are always just sums of squares over degrees of freedom. And degrees of freedom are always just the number of values that go into that variance term minus 1. Again, I'm not going to walk through all the hand calculations for this example because that would make a long segment even longer, but we will put an example of hand calculations on the website. It's helpful sometimes just to walk through an example rather than just rely on R to give you the results. Now, you'll get those F ratios, but once you get those F ratios, you're not completely done, right? Because if you have a significant main effect, you have to follow that up with post-hoc tests to see where the pairwise comparisons are significant. You might do Tukey's procedure, for example. Similar idea with interaction. If you have a significant interaction, you have to follow that up to see exactly where the interaction's coming from. And the easiest way to do that is by doing an analysis of simple effects. So you can just conduct a series of one-way ANOVAs across one level of the IV. You might even be able to pull it off with t-tests, as I'll show you in this example. Again, these are NHSTs, so we want to supplement them with effect size. It's eta squared. There's one trick here in the factorial case. We could calculate eta squared one of 2 ways. One is called the complete, the other is called the partial. And most people will report the partial eta squared because it takes out the other systematic effects in your experiment. And let me show you that graphically. So here's the eta squared for, say, an interaction effect using the complete formula, which is typically not used, and I'll show you why here graphically. Hopefully this will come through. Is the eta squared is this piece relative to the entire pi. Well, that estimate of effect size is going to be impacted by the magnitude of the effect of A and the magnitude of the effect of B. I don't want it to be impacted by those other systematic effects. I just want to look at it relative to unsystematic variance. So in statistics, what we do is we partial out other systematic effects. That's the phrase that statisticians would use, is we partial those out. We did that in multiple regression when we wanted to control for another predictor, say. We just partialed it out of the equation. So now the formula is sums of squares for the interaction just relative to those sums of squares plus error. So this piece, the systematic variance due to A and the systematic variance due to B, those are left out of the equation. Statistically speaking, they're partialed out. The assumptions underlying the factorial ANOVA are just like a one-way between groups ANOVA. So we have a continuous dV, it's normally distributed, and we have homogeneity of variance. So to wrap up this segment, in the next segment I'm going to give you a full example. We'll walk through some results from R, but this is a long segment as is, so I want to just wrap it up here. With a factorial ANOVA, you're going to get 3 F tests, one for the main effect of A, one for the main effect of B, one for the interaction. You can look at main effects, interaction effect, and simple effects. Remember, we want to calculate effect size. We can do that with a complete or partial eta squared. We're going to follow up significant main effects with post hoc tests, and we're going to follow up a significant interaction with simple effects analysis. And finally, there's still that homogeneity of variance assumption because we're pooling variances from multiple independent groups. So we need to conduct Levene's test to see if we've violated that assumption. So that's the overview of factorial. In the next segment, we'll actually walk through that driving simulator example and look at the output from R.